Okay. Thank you to, and thanks to the organizer for inviting me. I'll speak today about topological insulators. I assume you all have heard about them, but I'm not sure, all of the students have really taken the trouble to find out what's about them. Now, currently, it's one of the most fashionable topics in condensed matter physics, with about 3,000 papers a year appearing with topological insulators in the title, and about 30,000 references made to topological insulators every year. This number has been constantly increasing over the last 5 years when the story started. I expect some saturation at some point, but so far it hasn't. Now, in 2 dimensions, it's also called a quantum spin Hall effect. And this name comes from the history of the subject. And maybe misleading. You'll see that as we go on. Now the properties. So in general, topological insulators can be in 2D or in 3D, and the properties are that you have that the bulk is gapped. But you have gapless edge states. Oh. Well, that the bulk is gapped, that's why they're insulator, and the gapless edge states is what makes them special, and those are protected by time reversal symmetry. Now, is that big enough for everyone to read, or should I write bigger? Who thinks I should write bigger? No one, good. And to illustrate what it's I forgot to mention here are my sources. There are 2 reviews of modern physics. One is a colloquium by Zahid Hassan and Charles Kane. Then there's another one by Shalang Shi and Susheng Zhang, and they both take different, they view the subject from different angles. So you can't read one and they cannot replace each other. And then there's a book by Andrea Bernevik, which is based on a course he has taught in Princeton, and which is of course also valuable. But of course, well, if you don't want to read a whole book, it's very good to look in the reviews, and on the subject they also they all contain details which are not in the book. In the book is more pedagogical. And right now, for an illustration of what a topological insulator is, I will limit myself first to 2 dimensions, and that will be for most of the lecture that I will be speaking about 2 dimensions. Now, you've heard from Carl-Jan, and may even have known before, how an integer quantum Hall effect, works. Or also, so integer quantum Hall effect is if you have an external magnetic field, but in the same universality class, in a sense, you also have the Chern insulator. And Carl-Jan has been speaking about both in extensively. So you have like a 2-dimensional strip here, and let's say we have some dirt here, and you have the edge state, and maybe I can find some colored chalk, yes. You have edge states which are chiral, meaning they go only in one direction. And to have that, the bulk violates time reversal invariance. And the edge states are of course protected because there can be no backscattering because there is only a mode in forward direction. So, you know, if there's some dirt, it will go around, and as Karlian has illustrated, it leads to a quantized Hall conductivity. So sigma xy equals n times e squared over h, where h here is Planck constant, and n is an integer, can be, well, for different directions of the magnetic field, can be anything. Is positive, of course, if it's positive for the direction of the magnetic field in one direction, it's negative the other way. So, and this is a topological quantum number and related to the TK and N invariant in band structures, and in the Chern insulator it's exactly the TK and N invariant. Now, the two-dimensional TI, or quantum spin Hall effect, TI, it works the following way. Well, to a very naive approximation, you have two copies of a Chern insulator. So here it's not driven by a magnetic field, and so here the magnetic field is zero, but T is violated in the Chern insulator. A bit more space. And the two-dimensional topological insulator, to a very naive approximation, is two copies of the Chern insulator with opposite violation of time reversal symmetry, once for downspins and once for upspins. So I illustrate it like this. Now you have the upspins, same story as we had on that side. But then you also have the downspins. And well, under time reversal, upspin maps into downspins, and right mover maps into left mover. So the downspins are just moving the other way. And so you restore time reversal symmetry by taking two copies of the Chern insulator. And the effect is driven, and we will see that in detail in the example I will give you, driven by spin-orbit coupling. I'll write it out once. Spin-orbit coupling has been known, of course, for almost a century, but it was always considered to be a small effect, a quantitative correction in solids. And with the discovery of topological insulators, it now has qualitatively changed the picture. So we restore T, time reversal, in the topological insulator, but the main thing, but a very important thing is sigma xy spin, which is given by jx up minus spin Hall effect. So you subtract the upspin current from the downspin current and divide it by the electric field. Here you just have current divided by field, And a question for you, just to see how much you know about topological insulators. You know this is quantized. Is this quantized? Everyone except Karl-Jan is allowed to answer. Is this quantized or not? Okay, well, you made a good, it was a good choice to come to the lecture. Now, you know, from the name quantum spin Hall effect, you would see quantum Hall effect, always the Hall effect was quantized. And first it was integer quantized, got a Nobel Prize. Was fractionally quantized, another Nobel Prize. And, you know, if the spin Hall effect would be quantized, you know, that historically it was, that was what people were hoping to find or were looking for. But to tell you the answer, it's not quantized. The name, you know, when I was a graduate student with Frank Wilczek, he always, there was a fractional quantum Hall effect, and we wrote papers. Karl-Jan quoted one of them. Frank always insisted on calling it the fractionally quantized Hall effect, because quantum effect can be anything, right? And it's really a quantized Hall effect, to be more precise in lecture, in wording. Now here, you know, history, I mean, it's a great stroke of luck that they didn't call it quantized spin Hall effect, because, you know, then they would have to change the name. So quantum effect can be anyway, so you can still call it a quantum spin Hall effect, even though the Hall conductivity is not quantized. So this is not quantized. But there's still a topological phase associated with it, and the invariant, I just, you know, if I would just like to continue on this blackboard what I have on the two sides here. While here the topological quantum number, here is n, is the number of chiral modes, where we count right moving positive and left moving negative, and that's element C. In the topological insulator, we have a topological invariant nu, which can be 0 or 1, and 0 is the trivial insulator, and 1 the topological. And trivial insulator means any insulator which can be adiabatically be deformed into an atomic insulator. Atomic insulator being, you know, when you have atoms and, you know, the electrons just don't form a band, like, you know, you have them all sitting there, everyone has its electrons close by. Then you can have a band insulator where they form bands, but the bands are separated by a gap, and the chemical potential is in between, so, you know, you don't get any conductivity. And those can be adiabatically deformed into each other. The topological insulator cannot be deformed into each other. And and what nu is roughly the number of, well, I use a word I explain, of Kramers pairs. This is a Kramers pair, upspin and downspin. A Kramers pair is a pair of states which map into each other under time reversal of edge states. They have to come in pairs because we have time reversal. So here I write that. So here T is good, and time reversal is the important symmetry in the game. Of edge states, pairs of edge states modulo 2. And this modulo 2 is also why it's not quantized. Now, why modulo 2? and that we have to understand, and I will go into some details. It's a very simple piece of physics, you know, so elementary that you say, well, you know, this you may for a moment you may think, you know, you didn't come here to hear undergraduate physics, but well, I'll force it on you nonetheless. So, you know, this was sort of introduction. Now my lecture really starts, and point one is I'll speak about time reversal and Cramer's pairs. Now, okay, time reversal. You know, you send time from going back, from going forward to going backward. Trivially, the position operator under time reversal, you know, remains the same. You know, I'm not going anywhere else if I stop time and go backwards. But momentum, of course, changes sign, and but from there you see that when I take the commutator between x and t, that must change sign. But we know the commutator is IH bar. So we see IH bar changes sign, and that can only be if I changes sign. So we see from here that time reversal must be some kind of unitary transformation times complex conjugation. And this is complex. Now, we can say something general about it. I'll leave it a little longer. Now, for the properties, if we take t squared, you know, just writing it out, it's u times k times u times k, and k times u times k is of course u star equals u times u star, and u is a unitary transformation, so unitary means u dagger equals 1. Then we have u times u transpose Hermitian conjugate, and Hermitian conjugate is like taking -1, so it's u times u transpose to the -1, and but t squared, when we apply it twice, I mean, the most we can get is a phase, because you know, we can flip time reversal, but then, you know, if we flip time backwards and we flip it forward again, so, you know, all I can get is a phase, because physical reality hasn't changed. So let's call this phase e to the I phi, and now with this formula I can write, if I solve that for u, I can write u equals e to the I phi, u transpose, just brought that to the other side. And now I plug the same formula for u transpose, so I get e to the I phi, u transpose, so I get e to the 2I phi u. And what I deduce from there is that e to the I phi is that e to the 2I phi is 1, or that phi equals plus minus pi. So the most we can get is a minus sign. And yeah, now I need more space. So we also see that t squared equals plus minus 1. Yes, and sorry. Yeah, no, I mean 0 pi. Well, t squared, this is, thank you, Carlian. 0 pi, I mean. Now let's look at spin. Now we know spin is an angular momentum, and therefore we expect that under time reversal it reverses. And if we choose a basis where s plus minus is given by s x plus minus I s y, and SC, so we choose a basis where SC and S plus minus are real, which is usually done. Then T is given by e to the minus I pi sy times complex conjugation, and it's easy to understand why. The complex conjugation will take the spin in y direction because of that minus sign. These matrices have to be imaginary. So, you know, if this is real, this is imaginary. So it changes sign under complex conjugation, and that is a rotation by pi around the y-axis. So this changes the direction of Sx goes to minus Sx, Sy goes to, Sc goes to minus Sc, but it leaves Sy invariant, and this one here changes Sy goes to minus Sy. And for spin equals 1/2, which is the case we are really interested here in, t equals e to the minus I pi half sigma y k, and that's minus I sigma y k, and written out in a two-component formalism with 0 minus 1 1 0 times k. So what time reversal does is, if I act with it on an upspin, I get a downspin, but if I act with it on a downspin, I get minus an upspin. And of course it leaves a singlet invariant. And now for Cramer's theorem. And that is, if we have a system where t squared equals minus 1, and that's the case for all kind of odd spins. Yeah, so maybe I should write here. So in general, t squared equals minus 1 to the 2s, where s is the spin. So for half integer spin, t squared is minus 1, and if we have that, then the single particle states come in pairs of time reversal conjugates. And for proof, well, we write t Yeah, or write that the other way around. Introduce T psi be time reversal acting on some state psi. And now if we calculate the overlap of two arbitrary states, T phi and T psi, then, you know, now I expanded on a basis of coefficients, Nm P U Nm K phi m star. So that's just this state expanded in coefficients. I have and I act with time reversal. So you know I take the unitary transformation and the complex conjugation, and here U N P K psi p. Now I can rewrite that as sum over MP psi p star. That comes from the complex conjugation. Sum over all n, I pull that n, u dagger mn. So here I have the complex conjugation, and if I also, in addition to take a transpose by interchanging the indices, I get a Hermitian conjugate, UNP phi m. Now, but you see this here is just U dagger U, and that's just a unit matrix, so this just gives delta m p, and so the entire the result then is I can write it as psi phi. This is on the left side because it has a complex conjugate. So that might not sound like much, but we can do something with it. So first let's take phi equals t psi and plug it in. Then on the left hand side we have t squared psi t psi, and on the right hand side we have psi t psi, and this is plus minus 1. So if t squared is minus 1, yeah, for we can even write here as minus 1 because so Kramer's theorem only works for that case. You see, so it follows that this equals 0 because you have minus it. It's minus itself, so it has to be 0. And so that means as each single particle state and its time reversal conjugate are orthogonal states. I mean, they cannot be the same state. And they're orthogonal. And the next thing here, we take phi equals Hamiltonian T psi, and plug it in, and what we get is T H T psi T psi. I forgot to mention something. Single particle states of T invariant Hamiltonian come in pairs of Because if you break T, then of course it's a different story. Is psi ht psi? But now you see what this side is really t squared psi. The Hamiltonian is time reversal invariant, so you can also write the Hamiltonian in between, t psi. And this side, you can also pull the Hamiltonian out, is psi Hamiltonian t psi. And t squared is of course -1. And you see from the equality here we have again the same expression. So we can which is 1 with a minus sign equals the same expression with a plus sign. So what follows that is also equals to 0. So said in words, if we have a T invariant Hamiltonian and we have so the single particle states come in pairs in Kramers pairs, and the Hamiltonian doesn't scatter them into each other. And that's exactly what is relevant to the two-dimensional topological insulator, because, well, it's the backward and forward moving states are Kramers pairs. So, you know, if we have, let me draw that. So we said we had forwards moving an upspin and backwards and downspin. And if we now have some impurity, a non-magnetic impurity, we are not allowed to break time reversal symmetry. There will be no backscattering because they cannot scatter into each other. That's what that says. So you can understand it by drawing a picture. And those of you familiar with Anderson localizations, it will ring a bell, but probably you aren't because you're field theorists. You know, the scattering can once happen like, well, I should change color here because, or do it in white. Well, I guess I change color. Because as you go around the spin, since you can only go backwards as a downspin, of course it has to change. Does anyone see what's wrong with this process? I just told you it can't happen, but you know, I've drawn it. It seems to happen. Any ideas? Everyone except Karl-Jan? Well, there's a second process. And the second process is the time reversal path. You know, you go like here, and then, so this goes this way. You go like that and come back like that. You can also do that. And since it's time reversal path, and you know, it's whatever the spin did in the first, it will, in the first pass, it will do exactly the reverse. So it will scatter like this. Now, when you look at those two paths, what's the relative phase in between? Once I have turned the spin this way, and once I've turned it this way. You see, so this path turns the spin this way from up to down. But this inner path turns this, well, I need some colors here, otherwise it's no good. So this is the spin, but we've got plenty of colors. So this path here turns it from here to here, and this path here turns it from, well, it started as an upspin, but then it went this way, so it turns it from here to here. So the difference is a rotation of the spin by 2 pi. And a rotation of a spin 1/2 by 2 pi gives you a minus sign. And that's why this backscattering, you know, the paths always cancel. And you know, if you're sort of, well, this a very similar thing gives rise to Anderson localization. But if you're not familiar with this way of thinking, and I assume, you know, just from your background in statistical field theory being the school about, you're not, this algebra, you know, you cannot deny. And that's what it leads to. And so, what protects these edge states is time reversal invariance, and that's why, you know, that's why there's a topological phase. And I want to make, since this is the essence of the topological insulator, I will want to make it even more explicit, now again in a language you're more familiar with, and show you, well, this is now already, this picture already belongs to point 2, which is absence of backscattering. In Ti. So if we write the edge state Hamiltonian minus IV sigma c dx minus mu, and here this is Pauli matrices, so it acts on a vector of upspins and downspins, and it just means the upspins travel to the right and the downspins to the left. So it's just, you know, it's an effective theory, it's just written this thing. So this is upspin, this is downspin. That's all there is, it's just 2 copies. I mean, you know, without that we have seen it before, that was exactly the edge states for the Chern insulator. And now we try to yeah, I should write that also in second quantized a second quantized version, because I need it for my argument. dk over 2 pi psi up dagger of k psi down. So upspin, downspin, then Vk sigma c minus mu psi up, psi down. Okay, and now we try to add a mass term to gap it out, and well, mass term would be m dk 2 pi psi up k. So a scattering between up and down spins, just what I told you here pictorially, that is forbidden, plus Hermitian conjugate. Now you see, when you do time reversal in time reversal symmetry, T H mass T would transform into minus H mass, because what you would do is you would take that into a downspin creation operator, this into minus an upspin creation operator, and then, you know, it would be the Hermitian conjugate term, but with a minus sign, so it would cancel out. So it's forbidden by time reversal symmetry. And that's exactly the same statement I made here and I made here. But you see it in the field theory, you try to write down the term, and it's odd under time reversal, and so it's forbidden. But when you do the same thing, if you have two edge modes, so compare with 2 forward upspin and 2 backward downspin movers. So you imagine, you have a churn insulator with churn number 2, which has 2 modes. What would happen? Well, then of course the total spin of the forward mode can be 1, and Cramer theorem doesn't apply anymore. And this formulation is good to see that you can gap it out. So the edge theory would be then we can have mu equals 1 to 2 for the 2 edges, and same theory. So we give them another index mu, and we have 2 edges, and same thing. I think you can put the details in, right? And now we consider a mass term, and now we have a new possibility to construct a mass term. Namely, we can write m dk over 2 pi psi up 1 k dagger psi down 2 of k. So now I have not the scattering from upspin to downspin, but it also changes the species. And now I make a minus sign, minus 1 up, 1 down of k, creation operator, an annihilation operator of 2 up of k, and the whole thing plus Hermitian conjugate. And now I have a possibility I didn't have here, because these 2 terms had to have the same signs here, because they were Hermitian conjugates of each other. Now they don't have to. So time reversal symmetry changes the sign of this term. I mean, time reversal symmetry maps this term into, well, minus this term, but it comes with minus, so it effectively interchanges these 2 terms. And what we find is time reversal. This, maybe I make here a 2 for the 2. So time reversal H mass 2 time reversal equals H mass 2. And I can scatter them. And if I scatter them, what will happen, lonely mode on the edge, any kind of dirt will give some backscattering. It's very, very easy to I mean, if a lonely mode at the edge is not protected by some symmetry, it gets killed immediately. So and that is why the spin Hall conductivity is not quantized, because when we have only one chirality, like in the integer quantum Hall effect, all these edge modes scatter in the same direction, so there's nothing to backscatter. Now we have backscattering, and so if it can backscatter, it will. So it's almost trivial, but except that if we have spin on 1/2 and just one mode, it cannot backscatter, and that's why we are in a topological phase. And that's why the topological invariant is only a C2 invariant. Okay, questions so far? I mean, if you understood what I said now, you have understood the essence of the topological insulator. Of course, you have to, if you had come to Carlian's lectures and found out about the Chern insulator, that's really the piece of information the topological insulator adds. Questions? Yes. Well, you have to make a very clean sample. You can observe it, and it has been observed. But you. Well, it says never zero, but it's not enough to spoil the effect. I mean, there's also always a quantitative. You can't. I mean, I'll say a word. I mean, it has been observed in mercury. Telluride, cadmium telluride quantum wells, and they have to be extremely clean, and you can't make the thing like a meter long, it's on a few nanometers and you just see the edge states. So, this is a quantitative thing. But if you make the sample small enough and clean enough, and technologically it's of course a huge challenge, but then you have it. So no, designing an experiment and carrying out this experiment is sort of just an unbelievable piece of physics. And this is really like state of the art of, and here in the quantum Hall effect, like the effect has been, it's also challenging to make these extremely high mobility inversion layers and people, well, in Würzburg from Klitzing, they have grown them, and then Horst Störmer made even better ones and observed the fractional effect. But the field was always driven by experiment. They found the fractional plateau and they said, oops, we had the TK and an environment, and it had an explanation why it should be quantized in terms of integers. But then the fractional effect came along. Here, the field was entirely driven by theorists, by theory. And even the experiment, was basically designed, by the group of Susheng Zhang, which is an unbelievable accomplishment. Because, Susheng Zhang has a field theory background. He can lecture you on topology, and got into semiconductor physics, figured out how to do it, and, got in touch with experimentalists, and it was still a huge challenge to do the experiment. But it's sort of, in my opinion, just one of the most remarkable achievement in physics I have seen. People always stumble into something, but here they didn't stumble. They thought and did it, and so it's not so it's a highly unusual field. Now, I have a few minutes before the break, and I'll just say a few words on point 3, which is TKNN and Chern invariance. Now, this is a great piece of physics. There are two things to be said about it. First of all, my time is limited, so I can't give you the full story. I would love to, because it's just icing on the cake. But it has all been eaten off by Carlian, and what's left has been scrapped off by Eris. So, I'm not surprising you with any result here. But let me just summarize what you have been told already. And that is that, and I summarize it for the two-level system, because that's all I will need. Where we can always write the Hamiltonian as some constant, some piece proportional to the unit matrix, and some vector h of k times sigma. Sigma is here Pauli matrices. It doesn't usually doesn't refer to spin, but just to the two levels. And this is just the most general unitary, it's general Hermitian, a 2x2 matrix you can write down. Only the eigenstates matter. You can introduce h hat equals h over absolute value of h, and it is considered as an Hamiltonian. Yeah, it's just h equals h hat times sigma, and that should give you the same Barry's phase. Actually, we won't even need that, but the result is the Chern number is TK and N environments is sigma xy equals N times E squared over H bar, and this is just summed over all bands, the Barry's phase you get by integrating around the Briand zone. And I don't go into that. I just so for a two-level system, if you only fill the lower bands, this is just the Chern number of the minus of the, you have two states plus minus in a two-level system. If the general and it's just the Chern number of the lower band, and for the two-level system, this Chern number is given by 1 over 4 pi times integral over the Briand zone dkx dky dh by dkx cross dh by dky times h. You have seen this formula before. Kalian had it on the board, and this is quantized to be an integer, and you can rather easily understand why, because if you it's a mapping from a torus, because the Briand zone is so it's a mapping from a torus to an S2 sphere, so from one compact surface to the other. And if you look at a little squared dky dkx, what it's mapped to on the sphere, well, so I'm not sure how good I'm in drawing it. The sphere, so it's mapped into some region on the unit sphere where h lives, and so while you go from some, let's say we have some point here, and the point is here, then when you go into the, this should be kx, when you go into the kx direction, of course you get, so I use color here, in the k, you get a piece here, and that is given by dh by dkx times dkx. So that is this length here, corresponding to that. That's what it gets mapped. And, well, this here, or, better would be to make it like this. Where's my blue chalk? So this piece here gets mapped here, and and of course, on the sphere, it's dh by dky times dky. So all these factors are just, what this area is mapped into. And then we have the h here, because we have a cross product here. That is, of course, orthogonal to the surface of the sphere anyway. But this keeps track of the sign, whether we move, we can move it sort of said, said if we go around here, we go around this way, or we go around that way. So, it keeps track of this. This doesn't change the amplitude here, but keeps track of the sign whether, we are on the inside or on the outside of that moving. But since this is a compact surface, and this is a compact surface, when we do that mapping, we have to cover this, but we can't cover it like 1/2 because then we would have a boundary. So this has to be an integer, just because we cover a closed surface with another closed surface. And, so this is sort of what Karl-Jan has already told you, but I just wanted to remind you of this formula because we will need it after the break. So I suggest we make a how many minutes break, Andrea? Filippo? 10 minutes? 10 minutes break. Thank you for your attention. So, okay, I will be very brief on the graphene band structure and the Haldane model, because you have heard it already from Karl-Jan. The Brillouin zone, so graphene has an hexagonal lattice, and the Brillouin zone is also an hexagon, and there are two special points, and I call them K plus and K minus. Maybe make them like this. Where we have Dirac cones, and this repeats, of course, in Brillouin zone. So here's K plus again, here's K minus again. And at these points, we have, so these are these momenta, K plus minus. We have two Dirac points. And the Hamiltonian, well, is written in sum over K. So this refers to, it's a 2x2 Hamiltonian referring to the sublattice A and B in real space. AK, C, B, K. You all heard that from Karl-Jan, but I write it once again so that the definition is clear. CAK, CBK. So A and B were the two sublattices in real space. And at the Dirac points, we have H plus, so capital K plus minus, which are these points in K space, plus P, which is perturbing around these points. So that will be roughly, and I call that just H plus minus of P, where P is now the momentum around expanded around those points, and that is V naught minus plus sigma x Py minus sigma y Px. And time reversal symmetry now maps Hamiltonian of K, general momentum K, into H star from the complex conjugation, and of course, well, momentum maps into minus momentum. And we have a second symmetry, and that is inversion symmetry. Sometimes in the literature on that subject called parity, but I'm not happy with it because it's not in an even number of dimension. Parity flips all but one dimension. So here it's really inversion symmetry, meaning xy goes into minus x minus y. So it's also rotate in the plane, it's rotation by 180 degrees. And under this symmetry, well, you interchange the sublattices. I would sketch the real space unit cell for that for you to see, but Carlian did that. So h of k inversion symmetry is, and you do that by sigma x because that interchanges A and B. And you also, well, by rotating by 180 degrees, you of course change also the momentum into minus k sigma x. So we see these Hamiltonians are invariant because of course you change the sign of the momentum, but then you also interchange the two Dirac points just because you go from here would be another k minus. So under this transformation k to minus k, so when which happens in both time reversal and inversion symmetry, you also change plus to minus. So here you change the plus and minus indices, so you change that index. You change the momentum here, of course. So, here that sign change and that sign change compensate each other. And the sigma y, you change here by by complex conjugation the sign, and here by sandwiching it between sigma x. So these two Dirac points, they map into each other, but the Hamiltonian is invariant. And both symmetries together protect the Dirac points, because if you consider a mass term, now at the two Dirac points, I say plus minus comma m equals, and some mass plus, which I give also an index, plus minus sigma c. Now we check how it transforms into under these two symmetries, and under time reversal. And what transforms, of course, what is relevant is how the matrix sigma c transforms. And sigma c time reversal minus 1. What happens to sigma c under time reversal? Nothing, of course. But the inversion symmetry, well, gets sandwiched between the sigma axis, and that of course changes the sign. So that goes into minus sigma c. And now we see when we have both symmetries, we can't have a mass, because time reversal symmetry requires the mass to be the same at both Dirac points, and inversion symmetry requires it to change sign. So by having both symmetries, we protect the Dirac points are protected, and that's why in graphene, you really have them. Now we can think so we need to break one of those symmetries, and Carlian has mentioned all that. So the first thing you can do is break inversion symmetry, keep time reversal symmetry. Then you have, if you break that symmetry, so you don't care about that, so you have the masses are the same at both points, m plus equals m minus. And that refers to the situation. What the sigma c does is, in that case, when it's the same, it just adds an on-site potential with a chemical potential with different signs to the A and the B sublattice. And Carlian said that. So that what happens when you have a material where you have different atoms on A and B sublattices, then you break the inversion symmetry, and you can acquire mass. But now we can look at that formula. What happens if the mass is the mass decides the mass is the sigma c term, and this is so the Dirac term itself has sigma x, sigma y. So regarding with this vector h coupled to it, that means it's in the plane. So when you are in the sphere, when you don't have a mass, you're just in the plane of the equator. Now, when you have a mass at the Dirac point, this will vanish because px and py is 0. So, if the mass is positive, you're on the north pole, and if the mass is negative, you're on the south pole. Now, in this case, at both Dirac points, you're at the north pole. So, you somehow cover the sphere, but you never reach the south pole and you reach the north pole twice. And that means, one Dirac point, you start at the north pole, you go, close to the equator, and then you go back and come back to the north pole again. But that means, you cover it once with you cover it half with a positive sign and half with a negative sign. So, unless you reach both points once, you haven't covered the whole sphere. And so we see it's topologically trivial. However, if you keep inversion symmetry and break time reversal symmetry, then this must be obeyed but not that, and m plus equals minus m minus, and then you go once to the north pole and at the other Dirac point to the south pole, and then so here C minus equals 0. It's topologically trivial, but here C minus equals, well, the sign, Carlian has given you all the formula. The sign depends on the details, but you get a topologically non-trivial phase. That's what I want to say. And a way to accomplish that, to break time reversal symmetry, as Carlian has shown you, is by introducing these hoppings with phases. That's the simplest way and a very effective way, and you get that phase diagram. Yeah. So there's conventions are different, but on the physics we agree. Yes. Right. Okay. Unfortunately, I want to keep this, so I will I want to show you one more argument why you get an edge state. Carlian has shown you one, Eres has shown you one, and but is this like getting edge states from topological invariance, or getting the Chakif-Rebbe soliton is sort of what is the theme here, and time reversal symmetry is important, but if you don't have the edge states, we had nothing to play with. So I still want to say a few words about it, but we'll make it short. So edge states of Chern insulators. And the situation we will consider here, or I want to consider, is that the mass m minus, we had these two masses, right? And inside the topological phase, so here we have the C equals plus 1, whatever, plus minus 1. So here we have the trivial phase, and the mass, we say the plus mass is always positive, so m plus would be larger than 0. M minus changes sign as a function of x and goes to 0 at x equals 0. And now let's look at our Hamiltonian, what it would give. In the Hamiltonian, we take p to minus I nabla, and we only consider the Hamiltonian h minus now of x and y and derivatives equals v naught sigma yx minus I dy, that comes from the py, minus sigma y minus I dx plus m minus, which now depends on x, sigma c, and written as a matrix, it's m minus v naught dx plus I dy, v naught minus dx plus minus m minus. And the solution to, one solution is readily written down, and this is the solution. Psi px, no, py, sorry, py xy equals 1, 1 e to the minus I py y e to the minus 1 over v naught integral from 0 to x dx prime of m minus of x. And to show you that that is in solution, we consider the action of v naught plus minus dx minus I dy on that piece here, because, well, this is trivial and we are acting once with a plus sign, once with a minus sign here on that piece. And what we get here is minus plus m minus, because the dx just, so of the exponential it brings down that with a minus sign, and then when we take the derivative we just get the, or that should be x prime, we just get the mass at the point x plus v naught py, which comes from that factor. And now you can put it in your head, put that in here with the minus sign, here with the plus sign, and you see when we multiply it with this vector, the mass cancels out and we just get that term. So we see immediately that that this is an eigenstate of H minus psi px xy with energy v naught py mal times the same wave function. So this is our energy E of py. And we also see that the state is, with this mass profile, is located rather sharply at the boundary. So it falls off, and as the mass here grows, it falls off even faster. So this is the state, and it's extended in the direction perpendicular to the boundary. And this is a very general finding, and something, you'll forget lots of things. I hope you remember from my course that there's only a C2 invariant in topological superconductors, and the spin Hall conductivity is not quantized. And what you should remember from this school at large is that whenever you have a Dirac Hamiltonian and it's gapped and the Dirac mass changes sign, you get a gapless mode, Chakif heavy soliton, and that is very, very universal. And you must get a gapless mode because, well, when the signs, when you change one, as Carlian told you, you have to have two Dirac cones because otherwise you can't match the periodic boundary conditions. So, if they both have different signs, you cover the sphere and, one changes sign. So you lift it up here and you change the topology, you change the Chern number. And, since you're in a different topological class, you cannot go from one to the other without closing the gap. And what's the cheapest way to close the gap is having a gapless mode. So that's how you get it. And that's a very general piece of physics I would like you to remember. Okay. Now I still have a lot to say. So we are clear on that, right? You knew that anyway. But it's sort of extremely simple how it comes out here. And now more challenging topics which you didn't know and which unfortunately, I will be only able to say so much about it. And that is about, how it's realized in the semiconductor quantum wells. So 2D TI in mercury telluride, cadmium telluride quantum wells. So this experiment is sort of what really got the field going. That and it's a fantastic piece of physics. And I'm at Würzburg, so it's just I just have to take the elevator and move a little bit horizontally, and I'm right there. So at semiconductor physics, I sort of gather is not your subject. So but I still have to. I still want to get the essential physics across. And it's when I was a student, like semiconductor in Italy, I guess you don't teach it a lot, but it was considered it was boring physics, semiconductor physics, and here it just isn't. So. Bob Laughlin, by the way, was trained as a semiconductor physicist. Did a lot of band structures in his graduate schools. And so was Danghai Lee, who is also one of the most, in my opinion, one of the most creative physicists alive. So, you're in semiconductors, you have certain bands. So here, what I've drawn for you is basically, it's relevant here because it's the band structure in cadmium telluride, and it's basically a gallium arsenide structure. Even so, unfortunately, that means nothing to you. So you have bands here, and I'll tell you a little bit. They have numbers and symbols like everywhere in physics. Here, this is S-type conduction band, and S-type, and it's a spin-orbit coupling, so J, the spin is not a good quantum number, neither the orbital quantum number, but they're coupled, and so it's a J equals 1/2 band with M equals plus 1/2. So, and you have a P-type conduction band, and here J equals 3/2. I will have to say a little bit more about it, and it splits into M equals plus 3/2 and M equals plus minus 1/2. So this is a very gallium arsenide. You've heard of that, right? a very conventional structure. And then you have mercury telluride. And in mercury telluride, something like a band inversion happens, but it's not the band inversion we are looking for. I'll show you what happens. The gamma 6 band goes below the gamma 8 band. So it's like here. And the gamma 8 band splits. And you know, here I have to say I'm always at the gamma point, and that means k equals 0. So I'm expanding around there, and here too. We have here m equals plus minus 3/2. Here we have, of course, m equals plus minus 1/2. And the gamma 8 band, so the chemical potential, well, I should really close that in here, because the chemical potential, there's no splitting at k equals 0, and the chemical potential mu just goes right through, because like same number of electrons, so 2 bands occupied, 1 empty of those bands I have drawn. So this is the gamma 8 band now, and this remains p-type, this remains s-type. And this is what is called a zero gap semiconductor, because the chemical potential, this is filled, this is empty, you don't have a gap. Right. And now and what we consider now, or what actually the group around Susheng Zhang and Andre Bernewig, who was his student at the time, have considered is a quantum well of those. So here's our gamma 6 band. Outside here is cadmium, cadmium telluride. In this region here, we have mercury telluride, but it's not an extended region. It has some widths, which will turn out to be of importance. And here we have cadmium telluride. And I'll make the p-type band, I'll make it red. And that is the gamma 8. And I told you, they have interchanged position, and that's what happens here. I think I make it a little bit, just for ease in drawing. Now, this is not actual numbers what I'm playing, but I make the drawing so that I can explain the concepts. Oh no, it's a good red chalk. I should put them here. Now, what happens is, here from the gamma 6 band, well, of course, in the potential well, we get bound states, and because you're locked into this, so this is the c dimension. Now on, and here's 0, and here we have a thickness d. And we assume now we have it, the way I draw it, it's above critical thickness. I say in a moment why that is of importance. So we have one level, we have a electron-like level H1, and then we have a hole-like level, and there it's reversed because the potential well, the quantum well is reversed, and that we call H1, and that is sort of the whole. It's a heavy hole band coming from the gamma 8 band, but now it's hole-like. And what this band really is, this H1 band, it has m equals plus minus 3/2. And the states which that corresponds to is px plus ipy, so orbital angular momentum 1 in z direction and upspin, that gives the m equals plus 3/2, and then the minus 3/2 is just its time reversal conjugate. So in this whole system, time reversal is good symmetry and we'll need it, we'll amply need it. And the E1 band is an m equals plus minus 1/2 band. And now it's a little bit more complicated because we have some linear superposition of coefficients which we won't care about, of having the S-type band, meaning the gamma 6 band with upspins, or the P-type band, Px plus Ipy, which has m equals 1. I mean, Pc, the quantum, the c direction quantum number equals 1. But then, we add a downspin to it, and then we get 1/2. And here, of course, the Hermitian, the time reversal conjugate. Minus downspin. Upspin. And probably another sign, minus sign, because we turn the spin here. But whatever. I mean, the only thing what is important here is this band is a superposition out of the 2m equals 1/2 bands, because they hybridize. And of course we get a second band, but we have a linear space, we get a second band, but this is not of importance here. The number 1 just refers to that it's the first bound state. Here there will be other ones in the potential well. And we have a situation where the chemical potential is in between here, and only when the thickness is above a critical thickness, the H1 band is above the E1 band. If we make it too small, the smaller we make, the higher we push this up, and the more we push that down, and so these levels cross at some distance dc. And now let's look at the Hamiltonian. Yeah, I guess I won't need that here. So first of all, the basis we consider here, I can write that here. We consider here will be consisting of 4 states, and I leave now just for ease in notation. I leave the ones away because I will need some E plus H plus E minus and H minus. And these are, of course, exactly these orbitals here. And the E's are Kramers pairs, and the H are single particles are Kramers pairs, but there are matrix elements in between those and in between those. But there are no matrix elements between the plus and minus sectors. So we can write the Hamiltonian. And one important observation about the Hamiltonian is that since they have different orbital angular momentum, or different values of m, the matrix elements coupling those and those, I write that down, They have different m, and with that they also have the opposite parity or inversion symmetry, and so E1 plus minus and oh no, I don't want the 1, and H plus minus have opposite parity, and we have delta m in the z direction equals plus minus 1. So when we in any scattering element, we must take that into account, and therefore the off-diagonal elements connecting them must be proportional to kx plus minus I ky, because I need to connect states with different MC, and so the matrix element must also have opposite odd parity. Otherwise, I can't do it. While the diagonal elements must be parity even, and that means even powers of k. So the Hamiltonian has also around k, expanding around k equals 0, the Hamiltonian, and I write here this is a 4x4 matrix in this full space, will have the form h of k, and here h star of minus k, which is just the time reversal conjugate, 0, 0, and these are 2x2 Hamiltonians, where h of k will be given by some epsilon of k times 1. So, form we have here, plus some Hamiltonian small h of k times sigma, and this will be, I'm using the parameters from the original papers. I'm not a band person myself. C minus d kx squared plus ky squared. And this will be, well, we have said the off-diagonal elements, those multiplying sigma x and sigma y here, have to have this form. So we have here some a kx minus a ky and m plus b, difficult to read, plus b kx squared plus ky squared. But now you see, this is effectively a Dirac Hamiltonian, and this here decides the mass. And now what we see is, as we go to large k, well, we always have something. So for b, so b is always larger than 0. So we go. We are not, well, for large k, we are at least not reaching the south pole. This is, of course, an approximation around k equals 0. So the story here is not complete, but the physics we need is there. And what happens in the quantum world is, as you manipulate the distance, this E1 level comes down in energy. Oh, E1, whatever. I left some one away, but I didn't do it in my notes, so it keeps appearing. And the H1 level goes up. And what will happen, there's a crossover. When the E1 level goes below the H1 level, which is this situation here, which I have drawn, and at this point, DC here, the mass changes sign. Because that is a constant term, and that's a term which decides it's a sigma c. So, for one sign, this is above z, and it's 0 when they cross, and when on the other side, it has the other sign. So here, in this region, for smaller distances, m is larger than 0, and then has the same sign as, if I go far away. And here I have m smaller 0, and then you see now at the point, at the gamma point, when I have that smaller 0, I'm at the south pole of the sphere. But I'm only once at the south pole of the sphere, because then the band takes off, and it closes somewhere. But that is not how it closes, and when it reaches the north pole, and it must reach the north pole, is not in the formalism I've written to you. But what is I reach the south pole exactly once and then go away. And I know, I have a Brillouin zone, and somehow I close it. And I don't have a boundary here, and I don't come back to that point. So I close it exactly once. So this is the regime where we can tell. So here, C minus, our Cern number is 0, and here our Cern number, C minus, is plus minus 1. We don't worry about signs here. But so here we are in the topological phase. So, so we of course, we don't have we use the band inversion to sort of mimic Dirac physics. And the main thing is that here at that point that the Dirac mass changes, and that we can do in the semiconductor. And that's what the group around Su Zheng all figured out. And then doing the experiment, doing it very cleanly. And what has been observed is it's basically then a conductance measurement. The edge states, as Karlian has told you, give quantized conductance. It's just the one, you can write it as a Hall effect, but it's just when you have a sample. When you have some sample of it and you send a current through, you get a transport once from an edge state here, an upspin, and once transport from the downspin state here. So in total you get a conductance sigma of 2 e squared over h. And that has been observed as soon as you can calculate the thickness, and as soon as it was thicker than the critical thickness, they observed that conductance. When it's smaller, it was an insulator with magnitudes with a magnitude smaller conductance, like 10 to the 4 smaller. So there was nothing, and it also didn't depend on the thickness of the sample. So it can't be the bulk what has been given it. It's a fantastic experiment. The references, it's cited in the references I gave you. It's a paper by König et al. In Science from 2007. Okay. I have a few more things to say, but if you have questions on that, this is probably the part which is most challenging to an audience like you. I mean, other things you have seen, and you had already a chance to ask questions on churn insulators. But are there questions on that? If this is not the case, I raise the blackboard. Right, so we are almost done. I think I have something like 10 more minutes. What I haven't told you the three-dimensional topological insulators. Now, of course, the physics, well, it is more complicated, but it's conceptual, it's also a topological effect. And I will now switch to the simplest formulation of the 2D and generalize that just to tell you what this 3D is about. And that will bring me back to once more define the C2 invariant. So I think that would be point 7. Talk once more about the C2 in. And we already said, I mean, nu equals number of Cramer's pairs. Of edge states. Modulo 2, because each pair, even if you have two upspins moving in the same direction and two downspins the other way, you can have the scattering as I've shown you. And so this number can be 0, 1, and 0 is trivial. No, my R's are no good. And 1 is topological. Now, if we have a band structure with inversion symmetry, we have 4 points in the Briand zone. I paint here the square. We have 4 points where which are mapped to itself under inversion symmetry, and those are those 4 points here. Because the Briand zone is periodic, you can think of it as a torus. So this point and this point and this point and this point is the same point. So you have these 4 points, and when you write a band structure, you write it in Bloch states. If you haven't heard from them before, you did in Carl Jan's lecture. Um of k. And under inversion symmetry, at one of those points, lambda a, and so these are the points lambda a, and a goes from 1 to 4 in a two-dimensional band structure. Under inversion symmetry, what can happen is they can change sign or not change sign, because inverting them twice will give you, will take the sample right back, will take the system right back where it was. So this can only have eigenvalues plus minus 1 lambda alpha of lambda alpha, lambda a, sorry, lambda a. And now it turns out that if you don't have to do the whole calculation of calculating for all bands the Chern invariant, summing them up. You don't have to do the full TK and N calculation, because you can immediately from these numbers decide whether you're in a topological non-trivial phase or not. So minus 1 to the nu, and nu is limited to 0 and 1, but then you get here plus or minus sign, equals sum over a equals 1 to 4 over these 4 points. Product over a equals 1 to 4, product over m, and that's all filled bands. Empty ones do not matter. In a second I say something about it, of this xi m of lambda a. So if you would do that over all fields, of course you would, well, you would always get nu equals 0. I mean, everything you fill completely is trivial. But so you have to consider what the filled bands are. You could equivalently consider all empty bands. And you take this product, and when you get and when this all becomes -1, then you're in a topological phase. This works unfortunately only when you have inversion symmetry, but usually you have, and if not, then you have to do more work, and there are also criteria, but time is running out. Okay, so this is another way to classify topological insulators, and I will use that to sketch for you how a 3D topological insulator works. And there are two different topological classes here, and this classification is great to explain what they're about. So 3D topological insulator is 0.8. Um of k. The small u, m is the band index, and the of k. Um of lambda a, and these are these points here. Oh, yes, I'm missing an equal. Absolutely. Thank you, Andrea. Inversion symmetry. Inversion symmetry takes x, y. Which I had before in I don't remember where I had, but I remember that I had it. No, when we talked about the Chern insulator and the Haldane model. So under inversion symmetry. So maybe, but please, anyone, I didn't, when there's an equal sign missing and no one complains there's something wrong. Thank you, Andrea, for paying attention. It's clear now? And everyone, shame on you for not noting it. And shame on me for not writing it down. So yes, three-dimensional topo. This, sorry? It seems, Andrea, it seems. It seems, yes. It seems, but it is. You just have to take it on task. I mean, you can of course prove that is a criterion. It has been proven, but I don't want to go into it because I will use the last minutes to. No, it seems completely unrelated. You're absolutely right, and you're not supposed to understand it. You're just supposed to believe me, or not believe me, but or well, Andrea, let's talk about it because 5 minutes is the most, and I want to talk. We talk in private about it. Okay, because there's two types of 3D topological insulator, and one is weak topological insulator, and there's three topological invariants associated it, which I call nu x, nu y, and nu c. And what it roughly is, you take a 2D topological insulator, and you make a stack of them. You just stack them on top of each other, and of course, you get something 3D. And now if you have the Briand zone of the 3D thing, it will be a cube. No. And let's that just be a quarter of the Briand zone, just this thing here made into a cube, and then I have a total of 8 points, which map under itself under inversion symmetry. So here would be kx, here would be kc, pi, 0, and so on. So we have 8 points. Now, this topological insulator, what the criteria is, and since I don't want to run overtime, I just say it in words, of course, in each plane here, you will, making, so here's this nu x, this criteria is this formula for those two, Z sigma C. Nu C is the topological insulator where I stuck them up in C direction, and I satisfy this criteria here. I write it like this: -1 nu C is related to what I do when I take this plane, and I could just as well take this plane here. You will see in a minute why. And then you also see what the others are. I can do it with this plane, I can do it with this plane, and wherever plane, when I go around, I have a minus sign. These are independent topological numbers. But they're weak topological insulators in the sense that when I have edge states here, of course, I never have one right moving states because there's a continuum of them. So they will scatter, so they will gap each other out. So, they're not very interesting, but it's a topological classification, and, for completeness, I mention it. But it gives me a very nice way to at least mention, because, I'm running out of time, the strong topological insulator, and what that is, -1 nu naught is the same formula with a equals 1 to 8 with all 8 points. That I can also have, and that makes and you see, when I have the weak topological insulator having this, since I have the same here, I have the same here, the number when I take this product over all 8, it will always be even. So, the weak, so whether I have a weak topological insulator, I can have it on top of the strong one, but that itself will never give the strong one. And the strong one is interesting because now I have protected at edge modes, and I want to show you very briefly what they are. So the strong topological insulator has edge modes, and what they have as or surface states is a single Dirac cone which has the spin tied to momentum. So you have here the plane. So here's kx, here's ky. And the spin you have only a single band, but it has spin, but it doesn't have upspin and downspin. The spin is determined, and it's for a negative solution, it's the other way around. So spin is tied to the momentum. And since I promised on my abstract I would sketch the effective field theory, I write it down. It's Vf n surface normal sigma. Now sigma is spin index, real spin, cross k. So you have a single Dirac cone, and you can have it because it is. You couldn't have it enclosed in a 2D Briand zone which you close, as Karlian explained. But here you do have it, and need to have it because you're going from a topologically trivial to a topologically non-trivial phase as an edge state. And I would love to tell you a little bit more about it, but since time is up, I think it's time to thank you for your attention. Questions? No, it's orthogonal to k. So k, when you're in a Dirac cone, k goes in this direction. K goes back goes away from the. So k is in the surface and sort of points away from the origin in k space, and the spin is orthogonal to it. So this is surface normal. So this is spin, and this is surface normal. Yes, has also been observed in angle-resolved photo emission, and a great review on that is a review by Kane and Hassan, because Kane and Mille identified the C2 invariant, and Hassan, in Bismuth antimony components, you don't have to engineer anything. You just have to look at the surface and you see it. Well, of course, with spin-sensitive ARPES means angle-resolved photoemission spectroscopy, and it has been observed and published in Science. There's beautiful pictures in the review. And actually, it has been observed. Something funny on the surface had been seen in ARPES for years and years. But unless you closely look and sort of know what you're looking for, you think, oh, some surface effect, and people just didn't pay attention to it. But it was implicitly in the data already a long time ago. People just didn't know what to do with it, and it also didn't seem important, and so it was just sitting there on the shelf. Absolutely. Well, the work by Zahid Hassan's group in Princeton, certainly. The work before, was only experimental, but it wasn't particularly striking, and but if you look, of course, then people went back and say, oh, now we understand, this. But I don't. But there, it's a three-dimensional topological insulators. There are a bunch of them you just take off the shelf. And what always is driving it is spin-orbit coupling, and that's why you see conferences on spin-orbit coupling. Unless you're familiar with topological insulators, you think spin-orbit coupling. Are we going back in time and doing old-fashioned corrections? But this is all about topological phases. Yes. No. Well, two of them can gap each other out, but one will be left single. And yeah. No, you could, well, do the exercise, you can't do it. But a simple answer is, when I had the Kramer's pairs, I told you, total spin, t squared is -1 to the spin. Two times spin. So, if I have spin 3/2, you see it's odd, and then it's -1. So you can, on the level I've shown you, you can do the exercise. Try to gap them out. You can't do it. And there's a deep reason for it. You have to have t squared equals -1 for the whole thing to work. But thanks for the question. At least, you paid attention. More yes. Well, in private. It's late, and we'll have the chance. Yeah, we'll have the chance.